You know the exact feeling. You've got everything loaded in your cart, you finally hit pay, and for a split second, there's that familiar, suspenseful tension. It's just a little spinning wheel on your screen, right? But in that moment, you're mentally calculating your bank balance, you're praying your internet doesn't drop, and you're just hoping the merchant's site doesn't completely crash before the order confirms.
But have you ever actually wondered what exactly happens in those 50 milliseconds after you click pay? Well, today in this explainer, we are going completely under the hood of a system that absolutely dictates our daily lives while remaining entirely invisible to us. We are looking at Razorpay's Vulcan. This is a pioneering AI architecture that is completely rewriting the back-end engineering of digital payments in India. It's basically turning that suspenseful wait into a frictionless certainty.
All right, let's dive into our roadmap for this explainer. First, we'll cover 1, the flawed payment pipeline. Then, 2, money's foundation model. Next up, 3, why transformers, followed by 4, translating payments into tokens, and we'll wrap up with 5, flash sale speed under 50 ms.
Okay, kicking things off with Section 1, the flawed payment pipeline, or, as we're going to call it today, the 3 blind models.
So before Vulcan came along, traditional payment gateways ran on what is essentially a totally disconnected reactive system. Imagine 3 brilliant experts in a room trying to launch a rocket, but they're locked in separate, soundproof booths and aren't allowed to speak to each other. One model independently checks for fraud, another frantically monitors to see if the banking gateway is down, and a third just kind of guesses if your OTP text message will arrive on time. Because these models act in complete silos, they rely on rigid, hard-coded rules to stitch their decisions together. It's clunky. Vulcan changes the game completely. It replaces those isolated experts with one shared intelligence. In a single pass, it evaluates roughly 3,000 transaction signals. Things like your card issuer, the current network latency, your purchase history, the whole shebang. It's predictive, not reactive.
Which brings us to Section 2, money's foundation model. We really need to talk about the sheer scale of the solution Razorpay built.
Look at this number, 3 trillion. That is, honestly, a mind-boggling amount of data. That's 3 trillion data points used to train this proprietary model completely from scratch. And to process something this immense, you need serious hardware. We are talking about utilizing massive H100 GPU clusters, built in partnership with NVIDIA and AWS. If you follow tech at all, you know H100s are the absolute gold standard for AI computing right now. It is incredible horsepower dedicated solely to this one system.
But wait, this next number is even more critical. 4 billion. Those 3 trillion data points, they represent over 4 billion actual, real-world digital payments. This model wasn't trained by scraping random internet forums or reading Wikipedia articles. No way. This is 4 billion real-world, hard-earned digital transactions acting as the core foundation.
Razorpay's co-founder Harshal Mathur put it perfectly. He said, "Vulcan understands the language of money." So instead of processing words or sentences like your everyday AI chatbot, Vulcan fluently reads the specific vocabulary of transaction events. This is absolutely crucial in the Indian digital payment network. Just think about UPI for a second and the incredible complexity of India's multi-hop payment ecosystem, where money has to ping through multiple banks and servers in just milliseconds. Vulcan is custom-built exactly to untangle that complexity. And the real-world impact of scoring all these events together, it's staggering. The quick commerce platform Blinkit is already running this live in production. Through smart routing, which basically predicts bank downtime to dynamically find the best path, transactions are seeing an 8 to 10% higher success rate. For fraud detection, it's catching 8 times more international card fraud. And how it does this is the cool part. Catching fraud at the network level by spotting behavioral anomalies across millions of events is entirely different and way more effective than just declining a suspicious card at the very last step of checkout. Throw in a personalized checkout experience that automatically suggests your preferred payment method, and you get a meaningfully lower drop-off rate across the board.
So how does it actually pull this off? Let's move to Section 3. Why transformers? Why do we need to view payments as dynamic sequences and not just static rows on a spreadsheet?
Let's break down exactly why older machine learning architectures just flat out fail at this massive foundation model scale. Traditional gradient-boosted models, like XGBoost, they treat a transaction as a static point in time. It's kind of like taking a single photograph of a moving car. You get a snapshot, sure, but you have no context about where it came from or how fast it's going. Standard deep learning models, like RNNs, are a bit better, but they process events one at a time. It's like reading a book word by agonizing word. which is just way too slow when you need to pre-train on billions of payments. But transformers, their underlying math paralyzes cleanly across those massive GPUs. Using what's called a self-attention mechanism, a transformer can read the entire sequence of a payment simultaneously. It understands the whole story, from your initial login session to a random bank hop to an eventual retry, all at once.
Let me give you an example to show you why this matters. Think about trying to buy tickets to a massive pop concert online. A 400 millisecond latency spike on a bank server might be completely negligible when you're just paying your electric bill on a random Tuesday. But in a high concurrency UPI flash sale relying on dynamic OTPs, where thousands of people are literally fighting for the exact same ticket at the exact same millisecond, that tiny fraction of a second delay is fatal to the transaction. Self-attention allows Vulcan to automatically weigh that specific high-stakes context and adapt instantly. You don't need a human engineer frantically trying to manually hardcode a rule for every possible scenario. This brings us right into Section 4, translating payments into tokens. How exactly do we build a new vocabulary so this transformer can read it? Here's the catch. Because of extremely strict data privacy and RBI localization rules, Razorpay couldn't just plug their data into a public LLM. Highly sensitive financial data absolutely cannot leave the building to hit an outside server like OpenAI. That's a massive no-go. So they had to build a custom tokenizer from zero weights on completely isolated private infrastructure. They translate raw payment telemetry into 3 distinct families of tokens. First up, categorical tokens, like bank identification numbers or error codes. These act a lot like words in a dictionary. Second, continuous signals, things like latency, transaction velocity, or total order value, which get bucketed into specific ranges. And third, graph identifiers, like your UPI virtual payment address. These actually preserve the physical topology of the banking network itself.
And how does it build this into actual learning? Well, it's kind of like predictive text on your phone, but on steroids. Vulcan learns through masked event modeling. It deliberately hides a token, say a final response code, and forces the AI to predict it based on the upstream context. It also uses next event prediction to anticipate a routing failure in a retried chain before that failure even happens. Finally, it uses something called contrastive trajectory matching. Simply put, it learns to group normal, healthy transactions very closely together in its mind. Because it knows exactly what normal looks like, anomalous fraud patterns stick out like a sore thumb instantly.
Of course, all this incredible AI sophistication means absolutely nothing if it frustrates you into closing your browser tab. Which takes us to our final leg, Section 5, flash sales speed under 50 milliseconds. The absolute need for speed.
This comparison brilliantly illustrates why Vulcan is so uniquely engineered. On the one side, a typical text LLM has 70 billion parameters, sometimes way more. But Vulcan? It's intentionally compact and shallow, sitting at just 20 to 150 million parameters. Why can it be so much smaller? Well, unlike a chatbot that needs to understand Shakespeare, world history, and Python coding, Vulcan only needs to speak one highly specialized language, payment tokens. Processing just 10 to 15 dense payment tokens instead of dozens of words keeps the computational costs strictly in check, ensuring it never ever slows down your checkout screen.
The engineering pipeline making this happen is phenomenal. To give you some context, Vulcan operates in windows of 2 to 15 milliseconds. That is literally faster than the blink of a human eye. To stay that fast, Vulcan pre-computes historical data in under 2 milliseconds using streaming pipelines. Then, incoming live requests are dynamically batched together in this incredibly tight 2 to 4 millisecond window just to keep GPU utilization perfectly maximized. Finally, the live routing and risk scoring hits the NVIDIA Triton GPU setup for only 5 to 15 milliseconds of actual inference time.
But what if something goes wrong? They built in a brilliant failsafe, a safety valve. Under extreme flash sale traffic, if ingress latency crosses roughly 35 milliseconds, a circuit breaker trips. The system instantly skips the full self-attention AI processing and falls back to a simple, cached routing matrix. This guarantees that your payment still reaches the bank instantly. So the crucial point here is that user experience and checkout speed must always trump AI processing. If the AI is running even a tiny fraction of a second behind during a massive rush, it just gets out of the way.
So, pulling this all together, Vulcan represents a massive paradigm shift. It is one unified AI backbone, predicting the very next event in a payment sequence, minimizing friction and blocking fraud. It all happens in those 50 invisible milliseconds we talked about at the very beginning, working entirely behind the scenes to make sure your journey from clicking pay to seeing success is absolutely seamless.
Which leaves us with this final thought for you to chew on. If AI can now fluently speak the language of money movement, parsing billions of complex events in mere milliseconds, what other massively complex back-end systems in our world are just sitting there, waiting to be translated?